Greetings everybody, we're back here with section 5.2 where we do a little bit more with exponents and scientific notation, and in fact that's what we do. We're going to introduce um, well I guess you can call it two, but it's really one property of exponents. Um, if you have something like a times b or even times c all raised to an exponent, that means you're going to do a, b, c times a, b, c times until you have n copies of a, b, c. Well, multiplication is commutative and associative, so we can rearrange all these factors. You've got three factors here, three here, n times. We can rearrange this so the a's come first, and then the b's come next, and then finally the c's come. In each case, we'll have n a's, and we'll have n b's, and we'll have n c's. So what we end up with is a to the n times b to the n times c to the n. So we can effectively, if you just bring this left-hand side down here, if we are multiplying the inside of the parenthesis, we can effectively distribute the exponent onto every single factor. Likewise, if we have like an a over a b all to the n power, well, that's an a over b times a over b times a over b. So when you multiply across the tops of the factors, you get a to the n over b to the n. Now, there's a warning that has to go here because it becomes very tempting to make a mistake. And I'm going to put this warning on a new piece of paper here, and I'm going to make it very large and very bold because I don't want you to make this mistake. So it's true that the exponent will distribute over multiplication. That's true. And it's true that the exponent will distribute over division. That's true. It is false that you can distribute an exponent over addition or subtraction. A minus b to the n does not equal a to the n minus b to the n. This is a very common mistake. This is bad. And it's common, and lots of people make it. It doesn't matter whether it's subtraction or addition. Oops, make the n look like an n. These are both bad. If you remember, if you let n equal 2, you've before done a thing called foiling. And when you had ab all squared, you had to think about that as a plus b times a plus b, and then you foiled. You did a times a is a squared. A times b, those were the outside terms, was an ab, and then a times b again was another ab. Then finally you got the b squared. Notice that when you correctly multiply this with FOIL, you get a middle term. You get the 2ab term. You don't get just the a to the n plus b to the n. So here you have a to the n is a squared, b to the n is b squared, but you get this middle term. This is correct. And this does not equal a squared plus b squared because you got that middle term. So don't distribute exponents over subtractions or additions. You'll get it wrong. But we're going to do them over multiplications and divisions, and they're easy that way. So we can just kind of take things at a leisurely pace here. We're going to start with some scientific notation. And This is how they're going to want you to do it in your science class. The idea is to do this calculation, and we want the answer in scientific notation. We do not want to write this thing out in standard notation, because with these exponents, that's going to be a huge number. Nobody could count all those zeros, and we don't have to. We can use properties of exponents to make our life easier. First off, we'll simply multiply the numbers. The numbers have a special name if you're keeping score. They're called mantisses. 1066. That happens to be the date of the Norman invasion for history buffs. And history buffs might also recognize, I believe, 1215 is the year of the signing of the Magna Carta. So here we have 2 times 7 makes 14. 10 to the 1066 times 10 to the 1215, as we saw in the last section, we'll add those exponents. 10 clear 1066 plus 1215, 2281. In other words, a 1 with 2,281 zeros after it. Now, we're not quite in scientific notation here, because the mantissa, the number out on the left, has to be between 1 and 9. And this is bigger than 9. This is 14. So what you do is you think of this as 1.4 times 10 to the 1. And we're multiplying that times 10 to the 2281. So now we simply combine the powers of 10. 1.4 times 10, multiplying powers of 10, we add them, we get 2282. So the exponents are really a way of keeping track there. They're accounting for how many powers of 10 you're multiplying by here. Same thing here, we have things in scientific notation. It's written with dots instead of with the St. Andrew's cross, and it actually, multiplication, it's not an X that you're using if you use it for multiplication. It's actually the St. Andrew's cross. It's different from the letter X. If we're multiplying this out, we can take care of putting the mantissas, the whole number part factors, separately. And then we have the factors of 10. Well, we have a 10 to the negative 7 times a 10 to the 4 times a 10. Since I've got the negative 5 on the bottom, that's going to be the same as a positive 5 on top. We're subtracting a negative 5. Then we have a 1.2 down on the bottom. So take care of the mantissas, take care of the factor out front. 2 times 7 is 14. Divide that by 1.2, and we get 11.667 times 10 to the negative 7 plus 4 plus 5. Well, negative 7 plus 4 is a negative 3. Negative 3 plus 5 is a 2. You get 10 to the 2. So you have 11.667 times 10 to the 2. This is once again a number which is bigger than 9, so we have to get it smaller. We have to get it between 1 and 9. That moves the decimal place once to the left, so that made this number smaller. The way we put it right is multiply it by a factor of 10. We move the decimal place once to the left. That made it smaller. Multiplying by 10 would put it back where it was, times 10 to the 2. So we have 1.1667 times 10 cubed. In your science class, you'll learn the rules for how many significant digits, how many digits you would show here. And in fact, they would have you write this as 1.2 times 10 to the 3 in your science class. So here, once again, with scientific notation, we have a product raised to a power. Well, if you're multiplying, if you've got factors, the exponent can distribute over each factor. So you would have 3 to the 3 power times 10 to the negative 5 to the 3 power. Now we'll have to think about this for a second. 3 to the 3 power is 27. 3 times 3 times 3. Remember, that's 3 to the 3 power, not 3 times 3. So it's 27, not 9. Now here, we have 10 to the negative 5 to the 3 power. Well, that means 3 copies of 10 to the negative 5. So that's a 10 to the negative 5 times 10 to the negative 5 times 10 to the negative 5. And that's the same thing as negative 5 plus a negative 5 plus a negative 5. So 27 times 10 to the negative 15. Well, we could have gotten to the negative 15 in one fell swoop. If you raise to an exponent, again to an exponent, so this is an exponent to an exponent, then you multiply the exponents. And in fact, this is an example of another property of exponents. I'll write it down on a sheet of paper in a second. We're not quite into scientific notation yet because 27 is bigger than 9. So once again, write that as 2.7 times 10 times 10 to the negative 15. Then combine the powers of 10. 2.7, 10 to the 1 times 10 to the 15 will be 10 to the 1 plus 15, negative 15, so it'll be 10 to the negative 14. So, another property of exponents. If you have a to the n all to the m power, so these are called nested exponents. And there's nothing else going along. There's no addition or anything in here. It's basically exponent, again to an exponent. Then that's going to be a to the n times a to the n times, you just keep going, a to the n. You've got m copies of all that. Well, that means you have a times a times a, you have n of those, and then you have a times a, you have n of those again, and then you have a times a times a, and you have n of those again, but you do all of that m times. You have m groups, each of them containing n. So you have m boxes. Each box contains n objects. So you really have a times yada, 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 yada. You have, all told, n times m factors. So a way to simplify this is simply multiply the nested exponents. So a to the n, all to the m. Multiply the two nested exponents. So for instance, a really quick example. If you had 2 to the 3 all to the 4, that would be 2 to the 3 times 4. That would be 2 to the 12th. And we could check this on a calculator. So I'll do the left-hand side first. Parenthesis 2 to the 3 all to the 4. And we'll get a largish number. Then I can do 2 to the 3 times 4. 2 to the, if I'm going to do multiplication in the exponent, I've got to protect it with parentheses on this calculator because the exponent is greedy. In order of operations, the exponent would go first, so you get 2 to the 3 and you get 8, then you multiply that by 4 and get 32. That's not what we want. We want to get this 3 times 4 put together, then use it as an exponent. We get the same 4,096. Likewise, if you did 2 to the 12, 4,096. So, nested exponents can multiply. Likewise, if you see factorization here, you can rewrite it as nested exponents. Remember, equal says these two things are the same. It doesn't mean go from here to here. It means that if you see this, you can replace it with this if you want. And if you see this, you can replace it with this if you want. They're the same thing. It's like 2 $5 bills equals a $10 bill. That doesn't mean that if you have $2 bills, you've got to turn it into a 10. It means it's the same thing. Okay, so here we have once again scientific notation. Remember the multiplication dot is the same thing as the St. Andrew's cross. And we're almost there. We've got a number times 10 to the power, but the number is wrong. The number is smaller than 1. So we have to get this number in the correct format. It needs to be 3.1. But we just can't write 3.1. We've got to somehow keep it equivalent to 0.031. Well, 0.031 is 3/100ths. That's 10 to the negative 2 because the 3 was in the 10 to the negative 2 place. So 10 to the negative 1, 10 to the negative 2. So this and this are the same thing. And what I've done is I've managed to get a number out front that's between 1 and 9. Then we're going to be multiplying times 10 to the negative 16. Well, leave the 3.1 the way you have it. Combine the exponents of the tens. Negative 2 plus a negative 16 is a negative 18. And now we're in proper scientific notation. So let's see. Once again, simplify polynomial-like things, and we once again want positive exponents. We're using that nested exponents property here with the distributing. This is a negative 1 to the negative 5 times and a to the negative 3 to the negative 5 times a b to the 0 to the negative 5 times a c to the 7 to the negative 5. I'm writing these dots in as emphasis that we are multiplying. They're totally optional. And I brought the negative out as a negative 1 on this example just to emphasize that negative as a negative thing is really a negative 1 as a factor. Also, if you're thinking, if as long as b doesn't equal 0, b to the 0 equals 1, so we're going to get a 1 out of this factor. You could go ahead and write it as a 1, and then you could ignore it. We are assuming that b does not equal 0, or else this entire expression is undefined. Well, but we'll see that the b will disappear out of this. And if you were paying attention and you're quick, you could save yourself some trouble calculating. Well, negative 1 to the negative 5. Well, the negative exponent means make a reciprocal. So that's going to be a 1 over. Then you're going to get negative 1 to the 5. If we take this one step further down, we're going to get 1 over negative 1. Negative 1 to the 5, since you have an odd number of factors. The pairs will multiply together. Negative 1 times negative 1 pair makes a positive 1, but there'll be 1 left over. So there'll be a negative 1. And then 1 divided by negative 1 is negative 1. So if we take this forward 3 steps, we see that we're going to get a negative 1. In the very last step, that will be just a negative out in front of the entire expression. In the second step, we have a to the negative 3, again to the negative 5. Those are nested exponents. So remember that with nested exponents, we multiply. So we're going to have a, and I'll go ahead and write this step in on this example because it's nice to have 1 or 2 examples where every bleeding step is shown. That way, if you get confused, you've got something to back up to. Once again, you've got nested exponents. So you're going to have 0 times a negative 5, which is going to be a 0. And nested exponents one more time. Negative 5 times 7, so it's going to be negative 5 times 7. So now we actually do what we said we were going to do. Negative 3 times a 5, negative 5 is a positive 15. Notice that multiplying inside the exponent, negative times negative, we're just doing multiplication there. That makes a positive 15. If you think about it in terms of exponents, this negative means make a reciprocal, then this negative means undo the reciprocal. If you flip a fraction twice, you're back where you started from. Here you're going to have b to the 0. Anything times 0 is 0. Over here you're going to have c to the negative 35. So bringing this stuff down, you have a to the 15. b to the 0 is 1, since we're assuming that b doesn't equal 0. And then this is going to be 1 over c to the 35 because they said they wanted positive exponents. So if you've got a negative exponent, shove it into the denominator, and that'll get us a positive. Now all we have to do is multiply across here and write things down in a simplified form. Well, 1 times anything is itself. Negative 1 times anything puts a negative out front. Then we have an a to the 15 on top, and a c to the 35 on the bottom. Since these are not the same base, we can't simplify the exponents. So this is done. Then, have pretty much the same thing, except that we now have a fraction. I'm going to speed it up and show just the important steps here. You have x to the negative 1 times the negative 8 because this exponent is nested and you're multiplying on the top there, so we can distribute the negative 8 through, and since the negative 1 and the negative 8 are nested, we will multiply them. Then we have y to the negative 3 times a negative 8. And then down on the bottom we'd have 7 to the negative 4 times a negative 8. So that gets us an x to the positive 8 on the top, a y to the positive 24, and down on the bottom we have 7 to the 32, which is probably going to be an incredibly gross number. 7 to the 32, it helps if you turn the thing on, 7 to the 32. Yeah, that goes into scientific notation with a fairly large number. Notice the representation of scientific notation. You got the little tiny 10 to the down there. So this is not 1.104. This is 1.104 blah, 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 times 10 to the 27. That's mathematics best done in the privacy of your own home. I would just leave this as 7 to the 32. That's more meaningful. Let somebody else deal with the large number. Same thing here. We've got a product in the denominator, emphasize it with a little dot, and we're raising all to an exponent. We can distribute the exponent, and since these exponents will be nested, we'll multiply them. 5, negative 4 times negative 6, x to the 1 times negative 6 is negative 6. Remember, x without an exponent is really x to the 1. And then y to the 9 times negative 6. So we'll end up once again with 5, a rather ordinary number, raised to a rather large exponent. Negative 4 times negative 6 will be a positive 24. X to the negative 6, y to the negative 54. We're not supposed to have negative exponents. So we rewrite this answer. Anything with a negative exponent changes positions in the fraction. If it's on the bottom, it goes up. So we're going to have 5 to the 24, x to the 6th. The negative on the bottom is going to go up, y to the 54. And then we're done. And like the last problem, we're not going to try to expand 5 to the 24. We'll just get some incredibly ugly number in scientific notation. So what's the point? Combining a few properties of exponents here, we have an x to the 5th times this expression with an exponent. We'd like to combine the powers of x. That looks like it would be a good thing to do, but order of operations says we've got to deal with this exponent here before we can deal with this multiplication here. So the multiplication on the left sits there twiddling its thumbs while we distribute the negative 5 exponent through the product. Since it's the product in that parenthesis, we can distribute the exponent. We'll have x to the 5 times negative 5, y to the negative 5, z to the negative 5. So we'll have x to the 5 times x to the negative 25, y to the negative 5, z to the negative 5. Here we have a pair of like bases, so we can add the two exponents. A 5 plus a negative 25 makes an x to the negative 20. And we have 3 factors with negative exponents. So we rectify that, we simplify our answer by, since these guys are on top, anything without a fraction is considered the top of a fraction. These guys are on top, we'll shove them down in the bottom of a fraction. Since they have different bases, we can't combine their exponents. You can only combine the exponents like we did up here if the bases are the same. These bases are different, so they don't combine. Okay. Now, this is the same idea, just make sure that you read carefully. All of that is an exponent. Sometimes in my math lab, they don't write the exponents even this clearly, so you've got to read carefully. You'll get used to it after you've done a few problems, but that's all exponent, and these exponents are nested. So this is really x to the 3a minus 1, all of that, times 4. Probably what they want us to do for simplifying this, it would be fewer symbols if we go ahead and distribute the 4. So 4 times 3a is 12a minus 4. So this and this are the same thing. Now, that can happen when you have complicated exponents like that everywhere. So there's an exponent on the x, and there's an exponent like that on the y. At the same time, on the other x in the denominator, at the same time, on this y you have an exponent, and on this y you have an exponent. And all at the same time, we have a 24 divided by an 18. Well, 24 is a multiple of 6, and so is 18. If I divide both of these guys right now by 6, I'll be done with the number coefficient part. So I'm going to divide 24 by 6, and I'm going to get 4. I'm going to divide 18 by 6, and I'm going to get 3. So the numeric coefficient part is now reduced. Now, we have a 4/3, and we're going to have an x to the negative 2 minus 3a minus a negative a minus a 4. When you divide things with the same base, you subtract the exponents. Notice that I needed to put parentheses there. I needed to be careful that I didn't slip a sign here. I'm subtracting the exponents. That's where that minus came from. The negative stays on the a, the negative stays on the 4. I just kept those. And I'm going to do the same thing with the y's. Y 5a minus 1 minus a negative 5a minus 3. So these exponents each can be simplified because we can combine like terms. Since the exponents are in terms of a variable a, we have no way of knowing whether they are positive or negative unless we know what a is. So I'm just going to assume that I'm going to write it as though they're positive. This is going to be 4/3 times x to the negative 2. I'm combining like terms now, so it's going to be negative 2 minus a negative 4. That's the same as negative 2 plus 4. And then a minus 3a minus a negative a. That's the same as plus an a. And I'm going to do the same thing with the y's. There's going to be a 5a minus a negative 5a. That's the same as adding an a. Then minus a 1 minus a negative 3. So on top of this x, we have a negative 2 plus a 4 is a 2. Minus 3a plus an a is minus 2a. Then we have 5a plus 5a makes a 10a over top of the y. And then a negative 1 plus a 3 makes a plus 2. So that's simplified as far as it'll go. You could rewrite this in various ways, but this is a perfectly adequate way to express this answer.